All right, hello everybody. Today we're going to be talking about some sciencey stuff. I'm pretty sure everybody's familiar with computers. We all probably own them, multiple of them. But today we're going to be talking about quantum computers, which are pretty different. And Krysta, so I'm going to ask you my first question, which is, I've got an iPhone. I can order pizza with it. I can binge watch Stranger Things. Why should I care about a quantum computer?
Well, it turns out there's some problems in this world that we can never hope to solve with the computers we have today, right? Even if you take all the supercomputing and all of your digital technologies and put them together, there still remain problems that take lifetime of the universe timescales, even using all of that compute to solve. And these problems are really important problems for our world, for our society, right? Things like, how do we capture carbon from the atmosphere to help save our planet, right? How do we better handle clean energy, right? Also to help save our planet. And how do we do better food production around the world? Quantum computers can help with all of these types of problems that really do take, lifetime in the universe timescales to solve on digital technology, and then just a matter of, weeks or months on a quantum computer.
Which aspect is most exciting for you? You listed a few topics out there: the climate crisis, tackling that challenge, drug discovery. What is most personally exciting for you?
Yeah, well, most recently, actually just today, we announced some work we've done with Case Western Reserve University. And this is in the space of medical diagnoses, right? You think about, every one of us knows someone who has been diagnosed with a severe disease, whether it's cancer or multiple sclerosis or epilepsy. And in these technologies, we're working with Case Western Reserve University and Mark Griswold there to bring about revolutions in terms of MRI and magnetic resonance fingerprinting techniques. And with quantum-inspired algorithms, we can actually improve the speed of MRI, right? So the detection rates, you can actually have an MRI scan that is 3 times faster than it is today, and 30% more accurate. And this allows you to then pick out different tissues much more accurately, identify disease early, see if chemotherapy is working. And all of this is using quantum techniques to speed this up.
You used a phrase in there, quantum-inspired, which is kind of interesting because we don't have the hardware really itself, at least to a point where it's going to outperform what we have already. So what makes something quantum-inspired? How can we call it quantum if we're still running this stuff on classical machines?
Well, it turns out that we can actually look to quantum computing, and we can learn a lot from how those computers and those algorithms behave, and how quantum mechanics behaves, right? And we can take ideas from quantum mechanics and physics, and we can simulate them on our classical machines. And by simulating what these quantum mechanical behaviors are within, say, a classical algorithm, we can achieve speed-ups. And what's even better is once we have the full-scale quantum computer, we can take these same algorithms and speed them up even further using the full-scale quantum computer. So these are methods inspired by the full quantum algorithm, but that we can use today on classical machines.
So Andrew, this is also the bread and butter of your business. You're working on quantum software as well. Tell us what you're most excited about in terms of the potential applications of these algorithms.
Yeah, so for us, there's really kind of 2 different regimes that we think about. One is the regime that Krysta was just describing, where we have the ability to learn from the research that we're doing on real quantum hardware devices and to try and apply them in sort of supercomputing infrastructure today. And then the really exciting part, and I think what kind of gets most of our team up in the morning, is thinking about what are we going to do when we really get the first industrially useful scale machines that can really run based on quantum information.
When is that going to happen, by the way?
You probably have to ask Microsoft, but we're looking forward to it shortly. I mean, I think it's going to be relevant to the life of a young startup company. So we know that there are people who are building small devices right now that are important enough or useful enough that we can start to do kind of toy problems and experiment with mostly problems related to chemistry, kind of looking at the area where physics sort of zooms out and becomes chemistry. And if we can experiment with that much better, then we can understand a lot more about the physical world around us. And that's sort of everything from building better materials to doing things related to drugs to simulating the world at large.
So I'd love to get a little bit into the technology and understand better how it works. How many people in the audience have a PhD? Raise your hand. How about a physics PhD? Fewer. Okay, so we're on the same level.
Yeah.
Explain it to me like I'm 5, as they say. How does a quantum computer work?
Well, we could just get that guy to come up here, because I don't have a physics PhD.
I noticed, I was going to ask how many people have a quantum computer, but I noticed Dario Gil of IBM Research is in the audience, and he does have one, so I'd have to make an exception for that one.
I mean, the easiest way to think about it is that traditional computers are sort of based on this like classical understanding of the world, and we have these kind of fundamental components that behave very similar to how things behave at the macroscopic world. And those machines are capable of doing certain classes of problems that they're really good at. Because we understand that we live in this world that's kind of based around quantum information, we've been able to harness that at the lowest levels in order to build totally different classes of machines that can solve different types of problems. And I know that probably leaves a lot to be explained, but if you understand that really these are just devices that are built differently, that solve different classes of problems, that are extremely intricate pieces of engineering, to me, the how it works is interesting, but I mean, it's even fascinating to me how traditional computers work. I doubt many of us really understand how the phones in our pocket work. In some sense, that's exactly how quantum computers work. I don't know. But what can you do with them? That's the most important thing.
Krysta, add to this for us. Maybe you can provide some
She has a PhD.
But not in physics,
Yeah.
but at least in computer science, so maybe I can help. Yeah, so when we think about quantum computers, we're really harnessing the power of quantum mechanics and these amazing physical properties to bring together and then design an algorithm using these properties and really outspeed our digital technologies by incredible numbers, right? Billions of years. When you think about your digital technology, at the core you have a transistor. It's a switch, right? It's like a light switch. It's on or off. Everything in your digital, whether it's your phone or your laptop or your car for that matter, right? It's working on bits. And in the quantum computer, we work on something called a qubit, a quantum bit, which now instead of just being like a transistor that's on or off, we can design a more exotic transistor, right, that now can take on simultaneously both of those states, 0 and 1 simultaneously. And when you harness that plus these other amazing properties that perhaps people have heard about, spooky action at a distance that Einstein often talked about, or Schrodinger's cat, right, where there's a cat in a box and it's dead and alive at the same time. All of these properties we bring together, plus interference, to design quantum algorithms that bring, for some problems, billions of years of compute time down to just a matter of, seconds, minutes, hours, days.
I'd like to hear a little bit more about what this means for Microsoft. A little over a year ago, Satya Nadella, he laid out sort of 3 technologies that he was thinking about for the future. And he said, mixed reality, virtual reality, augmented reality, then AI, and then quantum computers.
Right.
Were you disappointed that quantum came last?
Oh no, I'll take that. That's pretty exciting to hear Satya, announce these 3 major investments in areas for the future of computing, and one of them to be quantum computing is, quite an honor to see it on that list, of course. And I do believe that it's a revolutionary technology, right? It's not just evolutionary. We're not just taking a step along the path to combating something like Moore's law, right? We're literally jumping onto another curve, and with this technology, hoping to solve some of the world's, the most challenging problems we're facing today.
It's been said to me that an abacus is more similar to an iPhone than a quantum computer is to an iPhone. Is that right?
Sure. Yeah. I mean, I think, in these technologies, what we're looking at when you think about quantum hardware, often they have to be operated at what we say millikelvin temperatures. What is that? That's almost absolute 0. It's colder than the coldest places in deep space, and you have to engineer these environments to maintain this really careful state of the quantum device, right? So these cryogenic environments have to be engineered to enable those temperatures, to enable the state to stay stable, and then you have to ask to interact with it, right? And I can't operate at almost absolute 0. That's definitely not possible. So we have to, part of what my team is looking at is how do you interact with that device? How do you get the control signals in? How do I program it as a user so that I don't have to know what the quantum mechanics, what that's all about? As a user, I just want to be able to use this technology for my applications. So we think a lot about that interface, the programming languages required, the compilation methods, and so forth.
And Microsoft has actually developed its own programming language for this, and you recently open sourced it. What went behind that decision to release that publicly?
Well, we, at Microsoft, of course, our mission is to empower every organization and every person on the planet to do more. And as part of that, we've seen Microsoft really opening up for more of a community approach to problems, to solutions. And so with that, we decided that we also want to see a broader community engaging around quantum computing, quantum algorithms, quantum applications. We know that we can't hire everyone in the world to help solve and identify the next killer applications of these machines and the ways that this will help our world. So we need to engage the community around this. And so we open sourced our quantum development kit, the QDK, which with it comes a QSharp, a quantum-focused programming language that we've developed so that you can easily write your applications for the quantum computer and for your problems. And so we announced this just this last week.
Andrew, do you use QSharp?
Yeah, absolutely.
What do you think of it?
Well, I think that, I should put this as a quick caveat. I don't do most of the quantum computing in our quantum computing company.
Sure.
But the team that we have, they've been really excited to both work with, and because of its open source nature, contribute to the work that's coming out of Microsoft here. And it really, for them, I think, they're the sort of very deep technical people who have the multiple PhDs, who understand everything from the ground up. And so for them, it's really nice to have tools that they can start to see what the future is going to look like, where in order to use a quantum computer, you don't need that deep background. It's really early days for this technology right now, so most of the people who are involved currently do have a very deep background in either quantum information theory or traditional just computer processing. But this industry is never going to be successful if everybody who touches one of these devices needs to have gone to school specifically to use that device for 10 years. And so the sort of real benefit that we get from things like QSharp is it makes this accessible to a much broader audience. And I think we've seen over and over again with technology that the most interesting things really come when you get the technology in the hands of many, many more people. And that's really what this is enabling.
Are there enough people to hire in this field? Like, are you getting the candidates that you want applying for these jobs?
Yeah, well, I mean, as much as I love to think of us as a very similar organization to Microsoft, the big difference is Microsoft has more lawyers than we have employees. So for us to have to hire up, we're just over 100 people right now. And because we started early, some would say kind of crazy early, we took a real bet that this technology was going to happen in the lifetime of a small company. But we've slowly built a team, and that team helps build itself by bringing in more good team members. So we've had really a strategy of exactly this: bring the best people together, have them kind of create a nucleus and grow it up. But even that, it took us 5 years in order to get to 100 people. So that's not a sustainable way to grow this industry. And I think that's a big thing. It's sort of an overlapping passion of ours, is to be able to grow that talent pool and to help that educational process to make it so there are more people who are capable of working in organizations like ours.
Right, yeah, exactly. I think both of us are working in our communities and the broader community to help educate people around what are the skills needed to enter this workforce. After all, this is going to open up what we think of as an entirely new economy, right? A quantum economy is coming, and we need to prepare for that. We need to prepare for that by training our workforce, and that's part of the reason for open sourcing the QDK and for encouraging the use of QSharp. We also have a series of exercises to make it easy to learn QSharp called the quantum katas. With all of these initiatives and these efforts, we're hoping that more people can engage around quantum computing. And with that, we can train a workforce that will be ready, right? Quantum software engineers, quantum developers. We also need cryogenic engineers, material scientists, right? We need people that can enter the field at all layers of this quantum computing stack. And right now, we are not in the position to have all of those people, right? We can't fill those roles because there are not enough people educated in this space. And luckily, recently, in late 2018, the United States government passed the National Quantum Initiative Act, which brings over $1 billion to quantum information science and quantum computing to invest in research centers, workforce development, workforce training, so that we're ready for this quantum economy and the quantum revolution.
That is an amazing bill that was passed, and at a time when you have Congress that is unable to agree on anything, Democrats and Republicans came together and passed this major funding initiative. So kudos to them. But I want to return also to Microsoft and its strategy, because one thing that is most interesting to me is that the company has chosen a different method of achieving a quantum computer than pretty much any other company out there. In a place that's already pretty sci-fi with respect to quantum computing, Microsoft is going into the depths and depths of the science fiction world here. And so how is progress going? And what is Microsoft doing differently than the other companies?
Yeah, it's a great question. And it's not fiction. Let's not go too far down the science fiction. It's definitely science. I'll give you that. But here we are really relying on a very new type of physics to bring about a very stable foundation from which one can build scalable quantum computing. And so at the core of a quantum computer, you have a qubit, right? That's in which you store your quantum information, you operate on your quantum information using this qubit. And it needs to be stable, it needs to be reliable, it needs to be able to hold that computation for a long period of time, enable a long algorithm to progress so that you get the reliable answer at the end. And so we're investing heavily in actually creating a very, very stable qubit, one that is orders of magnitude more stable than the other approaches to developing a qubit. And we call this a topological qubit. And the reason why we're investing so heavily in this is because we want to be able to reach problems that can enable us to study catalysis, to combat carbon capture, right, to help with food production. These problems require a very scaled up quantum computer. And so we need to be able to create qubits that are very, very stable. And so our approach is to really focus on that and bring about the new physics required to develop it.
And I know you've got the guy he was in charge of Xbox hardware and then HoloLens hardware. He's now working on this. But as I understand, Microsoft has not produced one yet, a reliable, stable, topological qubit, as it were.
Right.
How far off are we from seeing that?
Yeah, so it's a series of steps we take to develop this topological qubit. And the first is we actually have to show that this physics is right, that it exists. And so we actually had a series of designs that were developed, right, from the theory perspective. That in 2010, a series of theory papers came out. We then took that design, developed it in the lab, right? So one of our experimentalists in Delft took that design, made it in the lab, and within 2 years of taking the design and making it, was able to show that this Majorana zero mode exists, right? Could see the signatures of the physics we need. And then from there, we need to harness those physics and develop it into something that can hold information and compute. And those are the steps we're working on.
What is a Majorana particle, for those in the audience who aren't familiar? I know we all are.
Ready for a physics lesson? Yeah. So really, what we're harnessing is this kind of exotic property, this exotic type of physics. I won't get into the details here for this audience, but indeed, what it enables is an intrinsic protection of information. And so this type of qubit that we're doing actually is protected from errors. In an innate way, and that's kind of the beauty of this Majorana quasi-particle.
Now, Andrew, you don't have a horse in the race when it comes to quantum hardware, but if I forced you to pick your favorite approach, which one would you pick?
Well, if Krysta's sitting beside me, then I'd clearly say Microsoft.
Yeah, let's put topological off the radar then.
Honestly, it's the thing that makes our position interesting is because of the fact that we don't have the resources, and I don't think it would be an intelligent pursuit for us to go and try and build these machines. Instead, what we're really doing is saying it's incredible that there is this whole series of different choices that people can take. And so there are different companies exploring many different methods going forward. And some of the the options that seemed really exotic in the early days, like trapped ions, for example, was considered extremely exotic. And recent developments have shown that this is maybe not quite as exotic as people originally thought, or that there are many strengths of this method. But in some sense, the whole purpose of 1QBit is that we don't have to bet on any particular method. We're betting on the industry. We're betting that all of these resources being poured into all of these different methods will provide a winner, and that winner will be capable of running the software that we're developing. So in some sense, I just wish the best of luck to everyone, and I hope they all pour tons more money into it, because it's a necessary precondition for the success of 1QBit.
Got it. So I would like to open the floor up for questions in just a moment. I'm going to ask one more of both my panelists. What should people in this audience be doing to prepare for, as you called it, the quantum economy?
Right. Well, the first is to go and check out the QDK and try programming in QSharp. But I think also start to look at your businesses and the types of solutions you need. Already today, quantum with quantum-inspired algorithms has the ability to impact the solutions you need to move forward and to start developing this quantum economy. And so, of course, we have a Microsoft Quantum Network, which is a group of, 1QBit is part of it, startups and companies that are looking at quantum, quantum-inspired algorithms as well as quantum algorithms and how they're going to impact their business. And so definitely dive in, start learning about this space. Because it can help your business already now.
And Andrew, same question to you.
Yeah, I would just say that it's really easy to get kind of stuck in that question. We joked earlier about like who knows how these things work. But if you're really interested in the physics, then it's fun to dive into that. But in some sense, in the same way that you don't have to understand how an internal combustion engine works in order to drive a car, if you feel like it's intimidating to understand the real underlying mechanics of these machines, that's okay. It's not necessary to be a quantum physicist in order to take advantage of this. So what I would do is really pay attention to the types of applications that people are talking about. Every time that there's an event like this, people are going to talk about things like materials science, drug design, or optimization and other related fields as relates to the quantum-inspired optimization work that's happening at places like Microsoft. And in some sense, if you can understand the sorts of things that these devices are pointing towards, and you can understand whether or not this is really critical to your business, if you start to see a convergence there, it's probably worth reaching out and talking to some people to make sure that these technologies are going to enable your business as opposed to being sort of disruptive.
Maybe I could add one more piece.
Please.
Please continue to support and push STEM education in your communities, because that's how we are going to get a workforce that can do this.
We've got a question up front. Please identify yourself as well.
Yeah, Rick Chavey, Enterworks. The thing that fascinates or maybe terrifies, I guess it's in the quantum vein there, is the idea of quantum hacking and hacking of our banking system, our defense networks, our grid, and how do you think about that as it does start to rise up all the upside, but will we see a rise also of quantum hackers?
So our quantum computer is going to melt our encryption across the internet.
Right. Well, here's the really positive, great news, is that we know systems that are robust against quantum attacks. And this is a huge investment right now. Microsoft, governments, NIST is actually running a multi-year study where they've taken in a bunch of protocols, classical encryption methods, right, that they are looking at and making sure they're robust against quantum attacks, and then they're going to state, here's the one we're going to move to. That's happening right now, well in advance of the scaled quantum computer that can actually, break RSA, for example. And so we know there are post-quantum crypto methods, and we will move to those well in advance. And Microsoft has a large department working on that with Brian Lamacchia as the lead. So I want to reassure you.
The one thing that I would point out, though, on that is it's interesting because all of the things that we're sending today are being encrypted by these technologies that are weak against these future quantum devices. And so it really does behoove us not to sort of rest and wait for this to happen, because every day that we fail to take these steps, it really does continue to have us exposed. And it's not that this will be a problem when quantum computers arrive, it will be a problem until we switch to some of these methods. So even though it's nice to know that it's not the end of the world and that we do have methods against it, it's also something that we should probably take really seriously, and that is one of the areas that probably most of the businesses that are represented here, it might be their first exposure to quantum computing is upgrading their encryption methods in order to be strong against those future systems.
And Andrew's making a great point, right? To change much of the software, say at a company like Microsoft, you're looking at a decade to change that software over to a new encryption protocol, right? To identify all the places where, RSA might, components are called. And so to go in, we do have to make the software modular. We should do that anyway, because even RSA may be attacked tomorrow by a classical system. So we should make more modular software, flexible software, and we need to have companies aware of that and doing that today.
All right, excellent. We've got a question back here as well.
Hi, Joel Myers from AccuWeather. As you said, the quantum computer is going to be revolutionary and will actually revolutionize everything from medicine to understanding of deep space to every aspect of money and investments and warfare. And we do need to take it very seriously because, as I understand it, the Chinese are pouring far more money into quantum computing than we are, and by perhaps a factor of 10, obviously because of the warfare. And as you also mentioned, and it's important for everybody to realize that all this data that's been hacked can't be used yet. But if China gets the quantum computer before we do, they're going to make sense of all that data that's been hacked.
And is there a question that you have? Is there a question?
Yeah, what should we be doing? How do we raise the awareness in order to get everybody on board? It's almost like when we first went to the moon. I think we need to take it that seriously.
So how do we raise awareness about the threats to everything? Mostly sort of piggybacking off this question with encryption and intelligence and things like that. But how should you raise people's awareness about this and get them interested and excited and realize what's at stake here?
Well, I think a good step towards being able to see the development of quantum computing in our country, for example, comes with this National Quantum Initiative Act. I think that's a huge step forward for the United States. Other countries around the world, Europe has over €1 billion investment, the quantum flagship. That was all done prior, and it's great to see the United States come together. And as you said, this was actually a very nonpartisan issue in some sense. Everyone approved it, right? And that was exciting to see. So I do think that the awareness is, it is being raised right now, but we need to continue. I think it goes back to workforce development. We need to continue to think about how we're going to educate people in our country to be able to take jobs, enter the field where they can do really important technological advances here. And we need to be able to do the material science here. We need to be able to do, the software development here. And without people entering those fields and understanding what it means to even program, period, we are not going to be competitive. And I'll extend that to Canada since Andrew's Canadian.
Yeah, I was going to say, as a Canadian, I reserve the right to be equally afraid of China and the United States. So
it's wonderful.
But I feel like one of the interesting things is, despite the fact that I think the question was phrased in a sort of scary way, in a sense, really, these devices, what they share in common with the traditional computing revolution is that they're going to enable us to do lots of incredible new things. And so if we think about it as nobody wants to be left out of the process of having new tools that can allow us to build a new world, but in some sense, all the benefits that we're going to see from these devices, they're not going to be restricted to one geographic zone and one barrier or one area. So I think that we'll probably see that this is a technology that lifts all the boats, sort of a rising tide. And I suspect that there will be many focused national programs, but also I think that there will be global benefits from all of the techniques that are developed.
Certainly, if there is a chance that it can address the climate crisis, as you mentioned earlier, then it definitely will be a global thing, and everybody will benefit. But thank you both so much for your time
Thank you.
to chat about this today. Hopefully, you all learned something.